All right, exercise 23. The hypothesis in proposition 7.19b. I'm going to explain what this all means in my solution. So let's start by doing exactly what they told us to, because that's typically a good idea. So let mu n be delta n inverse minus delta minus n inverse. And mu be the zero measure. So if you were to think of this as like, this is 0, this is n inverse, and this is minus n inverse, then we've got a point mass, a positive 1 point mass at n inverse, and we've got a negative 1 point mass at minus n inverse. So let's see here. So this is a zero measure. I claim mu n converges to mu vaguely. But there is some x in R such that f is continuous at x and fnx does not converge to fx. Here, fnx is equal to the measure of the interval from negative infinity to x, and f of x is the same thing but for mu. And so it's going to be identically 0 because mu is a zero measure. So basically what proposition 7.19b said was that if mu n converges to mu vaguely, then at every point at which capital F is continuous, we have capital Fn x converges to capital F of x. And so this is a counterexample to that, because proposition 7.19 also assumed that this was a positive, that these were positive measures, I believe, or measures coming from positive linear functionals. I don't know. Whatever it is, it's not this. So, yeah. So we're going to go from here. To prove vague convergence, consider any f in C0R. By continuity of f, we know integral of f d mu n is equal to f n inverse minus f of minus n inverse. And we know that these things, as n goes to infinity, converge to f, well, this converges to f0, and the other thing also converges to f0. So that's 0, but that also happens to be the integral of f d mu, since mu is a zero measure, and hence, but that's an f, not a whatever weird looking thing it looked like. So this holds for every single f in C0R, and thus mu n converges to mu vaguely. Next, note that for every single natural number n, fn is continuous except at plus or minus n inverse. So fn is continuous at 0. Also, what is fn of 0? Fn 0 is mu n from minus infinity to 0, but that has to be precisely negative 1, since negative n inverse is in negative infinity to 0, and I'll write n inverse is clearly not in this set. But then the limit as n goes to infinity of fn0 is -1, because the limit of the sequence, which is -1 all the time, is -1. This is non-zero typically, unless you're in like, if -1 is 0, there's weird things happening, and you're working in a number system that you don't want to be in. But anyways, 0 is f of 0, since f is identically 0. So fn0 does not converge to f0. So hence positivity in proposition 7.19b is necessary. And this completes the proof.